Well, now we're going to return back to calculus. And you'll recall last term we introduced calculus, how we actually differentiate, how to find equations of tangents and normals, and that was pretty much all we did then. So let's just recap what the first derivative actually is, and there was different notations we could use for the first derivative. Y dash, or some people call it y prime, f dash x, d dx of the actual function that you're differentiating, or probably the most common of them all, the y dx. And it measures, when we're talking about the picture, the curve, it measures the slope of the tangent at a particular point. Because obviously with a curve, that tangent slope will change as we move along the curve. That's then useful when it comes to drawing curves and finding information about it, because if we know that that tangent is positive, then the curve must be going up. It must be increasing. And consequently, if the derivative is negative, that means the slope of the tangent is negative, so the curve must be going down, or decreasing, going down. And then if it's equal to 0, then it's stationary. The tangent would be horizontal, so we'd have a turning point at that stage. If it was a parabola, it would be its vertex. Let's have a look at this one. It's a cubic, 3x squared minus x cubed. We're going to find those stationary points and determine their nature, which basically means is it a maximum? Is it turning at the top, or is it a minimum? Is it turning at the bottom? So let's have a look. Our derivative is 6x minus 3x squared. Now when we're setting our working out, we don't just randomly write things down, we explain what we're doing, same as we would in a geometry solution, things like that. So, okay, the reason I'm finding dy dx equals 0, I tell them why. This is why I'm doing it. I know stationary points are going to occur when that first derivative is equal to 0. So that's the equation I want to solve. Simple little quadratic. I get two possibilities, x equals 0 or x equals 2. Now at this stage all we know is the first derivative. Later on we'll find different ways of doing it, but at this stage it's the first derivative. So we're going to investigate. We know the stationary points are 0, 0, so the origin, and 2, 4. Now be careful here. A lot of people make the mistake to find the y value of substituting back into the derivative rather than the y value. And of course, sub in the derivative, you're going to get the answer 0 because that's what you just solved. Okay, so make sure to get the y value you're substituting into y. So let's have a look at 0, 0. I'm just going to draw up a little table of values. So 0 is the point I know. So what I want to do is I'll pick a point either side of 0 to see whether the curve is increasing or decreasing at that point, and then I can tell what sort of stationary point it is. So I know it's 0, the derivative is 0, my tangent is horizontal. So I also like to draw myself a little line to give myself a visual picture of, oh, okay, tangent's horizontal. So I want to pick a point on the negative side of 0, and I want to pick a point on the positive side of 0. Now you can pick any point you like. Obviously pick something that's easy to substitute. As long as you don't go past any discontinuities. This curve doesn't have any discontinuities, so that's not an issue. Or any other stationary points. Okay, can't go past another one. So on the left-hand side, I'll just use -1. So then I like to write, okay, this is the number I'm using, -1. Sub that in, I get -9, so I know the curve at that stage is decreasing. On the right-hand side, I'll pick +1, substitutes, I get +3. So I now got a bit of a picture telling me what the curve does. It's going down, stationary, going up. So it must be a minimum turning point. It must be down one that turns at the bottom. Let's investigate 2, 4. Do the same sort of thing. I know at 2, derivative 0, so it'll be horizontal. I need to pick a point on the left-hand side, pick a point on the right-hand side. Well, it's obvious which one I'm going to pick on the left-hand side. I don't want to do extra work. I've already worked out 1, so let's use 1. And we know that's 3. So this time it's going up, stationary, and I'll just pick +3. And that has a slope of -9, so it's going down. So that one's going up, stationary, going down. Be a maximum turning point. I suppose the only other thing it could do is something like our basic cubic over there at the origin. If we were to test that one, it would have gone up, stationary, and then gone up again. And that's what we call an inflection point. In fact, that one would be what we call a horizontal point of inflection. More about that later. Okay, it's a very, very rough picture I'm going to draw. I know there's a turning point at the origin. I know there's a turning point at 2, 4. There, I didn't even bother finding the x-intercept, although it wouldn't have been too hard to find the x-intercept, would it? But there we go. It's a bit of a shocker. Very rough diagram, but it gives me an idea of what the shape's doing. So I know it turns there, it turns up there, and we've got a... It's all right. There's a recap and a bit of geometrical application of our first derivative. Time for you to play.